All right, continuing with solutions to the homework from page 238, and I had technical difficulties and had to start a new video. So we're on 13, and we want to find the first derivative and the second derivative. So the first derivative, okay, do you want to use the quotient rule or do you want to change this and use the chain rule? It's up to you. I'm going to use the quotient rule. So I have the bottom, x squared plus 3 times the derivative of the top, 0, minus the top 1 times the derivative of the bottom 2x over the bottom squared, x squared plus 3 squared. And we're going to simplify that. So we have negative 2x over x squared plus 3 quantity squared. Now we want to find the second derivative. So the derivative of the derivative, we're going to need the quotient rule again. So the bottom, x squared plus 3 squared times the derivative of the top, negative 2, minus the top, negative 2x, times the derivative of the bottom. Let's use a chain rule. So we bring down the 2, and we raise x squared plus 3 to the first, and then we multiply by the derivative of the inside, which would be 2x. And this is all over the denominator squared, so that would be over x squared plus 3 to the fourth. Now let's simplify this. Okay. Well, what do we want to do here? Notice that there's a factor of negative 2 in the first and the second halves of the numerator. And there's also a factor of x squared plus 3 in the first and second halves of the numerator. So I'm going to factor out negative 2 as well as x squared plus 3. And what I'm left with in the first term here is just the 1x squared plus 3 that we didn't factor out. And then what I'm left with in this second term here is the minus, the x, the 2, and the 2x. We factored out the negative 2 and the x squared plus 3. So that all works out to be minus 4x squared. Doesn't quite seem right. Is that right? Hopefully. Yeah, okay. And that is over x squared plus 3 quantity to the fourth. Okay, so we can simplify the part in the brackets. And that would be 3 minus 3x squared. Okay, now we want to find out what makes this second derivative equal to 0 and what makes it not exist, because those will be our potential inflection points, what I like to call pips. So whatever makes the numerator equal 0, oh hey, we can reduce this. Let me back up. Let's divide the top and bottom by one of the x squared plus 3's. Okay, that'll make the work a little bit simpler. Whatever makes the numerator equal 0 will be a potential inflection point, and whatever makes the denominator equal 0 will be a potential inflection point. So let's take the numerator and set it equal to 0. Divide both sides by negative 2. We could divide both sides by 3. Add x squared to both sides and square root, and we get plus or minus 1. And from the denominator, set it equal to 0. We can cube root it. Subtract 3 from both sides. And do you see what's going to happen? You're going to end up with imaginary numbers. So we're not dealing with those. Those are not part of our domain. We're just looking at real numbers here. So the only pips we get are plus or minus 1. So we're going to use those to break the number line into intervals. And we have negative infinity to negative 1. We have negative 1 to 1. And we have 1 to infinity. And we want to pick a number in each interval to test it. So let's pick negative 2, 0, and 2. And we want to test those into the second derivative to see if we get a positive or a negative, because that will tell us the concavity. So the second derivative is way back up here. here's where we're testing. Okay, so we have let's take -2. So plug it in, we get -2 times -2 squared would be 4 plus 3. You know, I'm just going to stop for a second and rewrite my second derivative in its reduced form closer to where I'm working so that it's more clear what I'm doing. Okay, going again, we're testing these points from each interval, and here is our second derivative. Now, notice that the denominator is always going to be positive because any real number you square is going to be 0 or positive. And then when you add 3 to it, it's going to be 0 or positive. And then when you cube that, it's going to be positive. So don't worry about the denominator. Let's figure out if the numerator is positive or negative. So if we take -2 and we plug it in for x, -2 squared is 4. 3 times 4 is 12. 3 minus 12 is negative. Negative times -2 is positive. Let's take 0. Square the 0, 0. 3 times 0, 0. 3 minus 0 is 3. 3 times -2 is negative. And when we do the same thing with 2, we're going to get what we got for -2 because you square 2, you square -2, you get the same thing. So what is this telling us? This is telling us that f of x is concave up, concave down, concave up. And that means we have inflection points at x equals 1 because there's a concavity change, and x equals -1 because there's a concavity change. And then the concavity, concave up for -infinity to -1 and 1 to infinity, and concave down for -1 to 1. All right. Next one. 15. Same directions, so let's find the second derivative. First of all, the first derivative, we need to use the product rule. So we have the first x times the derivative of the second. And to find the derivative of e to the -3x, we need to use the chain rule. So we have e to the something, e to the -3x, times the derivative of the something, so times the derivative of -3x, so it would be -3. So here we have the first times the derivative of the second, plus the second, e to the -3x, times the derivative of the first, 1. Okay, let's clean that up a little bit. So we have -3x e to the -3x plus e to the -3x. And we're going to have to find the derivative of that to get our second derivative. So I think what I'll do with that actually is to factor the e to the -3x out of it before I find the derivative again. So y prime is e to the -3x times -3x plus 1. Now let's find the second derivative. So we're going to use the product rule. So we have the first, e to the -3x, times the derivative of the second, and the derivative of -3x plus 1 would just be -3, plus the second, -3x plus 1, times the derivative of the first. And as we saw from the first part, the derivative of e to the -3x would be e to the -3x times -3. Okay, let's see what we can do with that. So we have a first part and we have a second part, and both of them have a factor of -3, and both of them have a factor of e to the -3x. So if we factor those out, the first term is just left with a 1 because we factored out everything, and the second term is left with a -3x plus 1. And to simplify the inside of the brackets, we have 2 minus 3x. So we want to see where that equals 0 or does not exist to get our potential inflection points. So let's set the first factor equal to 0 and the second factor equal to 0. If you have -3 e to the -3x equals 0, you could divide both sides by -3. E to the -3x equals 0. That's never going to equal 0, just like the e to the x function can never equal 0. This can never equal 0, so we don't get anything out of that. So then the other factor is 2 minus 3x equals 0. So 2 equals 3x, x equals 2/3. So that's our only potential inflection point. So let's take that and use it to divide the number line into intervals, negative infinity to 2/3 and 2/3 to infinity. And then we're going to test a point. So I'm going to test x equals 0 and x equals 1. We're going to test those into the second derivative. And let's go back to where we had our second derivative. Looks like right here would be good. Okay, so let's take 0. E to the 0 is 1. Negative 3 times 1 is negative. 2 minus 3 times 0 would be positive. So negative times positive is negative. Let's test 1. E to the negative 3 times 1 would be positive, times negative 3 is negative, and 2 minus 3 times 1 is negative, so negative times negative is positive. So we have f of x is concave down when the second derivative is negative and concave up when the second derivative is positive. That means we do have an inflection point at 2/3 because there is a concavity change. And then we can say concave up from 2/3 to infinity, concave down from negative infinity to 2/3. Oakley dokley. Number 20. Assume that the figure is the graph of f of x. Where do the points of inflection occur, and on which intervals is f concave down? Okay, so point of inflection is where the concavity changes. So it looks like the concavity changes at C. So I would say point of inflection would be x equals C. And on which interval is f concave down? Concave down looks like this. So that would be from 0, I guess, to C. If we're supposed to assume that it's going on infinitely far, then I guess we could say negative infinity to C. But the point is we can see that it's concave down until you get to point C. Okay, I think that takes care of the homework. Thanks, everybody.